Welcome to NARI Sim Center's Live Expert Tips. In this session, we introduce you to global sensitivity analysis for systems with high dimensional outputs. Our expert today is Dr. Song-Ri Yi. She is a postdoctoral scholar at UC Berkeley, where she develops novel methods for sensitivity analysis, multi-fidelity surrogate modeling, and adaptive design of experiments at the NARI Sim Center. She received her PhD in Civil and Environmental Engineering from Seoul National University. Her research interests include probability-based sensitivity analysis, surrogate modeling, structural reliability, and random vibration analysis. Song-Ri, welcome.
Thank you, Matt. Thank you, everyone, for attending this live expert tips. Before we start, I want to mention that all this method I will introduce today is implemented in quoFEM. quoFEM is a research tool developed in Sim Center, which enables users to run UQ and optimization analysis using their own models, like written in OpenSys or Python or any other simulation programs. So we have a nice user interface which helps you to first start the UQ analysis, but we are also open source project, so we open all the source code online, so you can always modify the code. And also we are looking forward to communicate with you through Sim Center forum. So today I will first introduce you to global sensitivity analysis very briefly, and then I'll talk about how we can apply those to high dimensional outputs. And then we will discuss about some of the algorithms we have in quoFEM, and then we will demonstrate this using a storm surge simulation example. So here we will provide two examples. One is material model structure example, and then the other is storm surge example. But we are interested in a black box simulation model, so really any model with input and output can be applied to whatever is discussed today. So we will start with the model with multiple parameters and multiple outputs of interest. When our input is random, then our output is also random, and task of UQ is all about quantifying this uncertainty in the outputs based on information we have about the input uncertainties. So UQ can be straightforward intuitively. We can run lots of simulations for the possible combinations of parameters, and then we will have idea on the uncertainty in the outputs. However, there are some challenges, mostly because our model is computationally expensive. So this limits the number of simulations we can perform to get the idea of output uncertainty. And therefore, we introduce some advanced or smart UQ methods, such as importance sampling or those using surrogate models. However, those methods typically suffers from high dimensionality, like the curse of dimensionality. So input parameter, we can have too many input parameters and too many output quantities of interest. And in that case, to make our smart UQ algorithm to work, we usually introduce dimension reduction techniques. For high input dimension, we usually perform sensitivity analysis to screen out unimportant parameters. So if there's a parameter that does not really affect the response, then we want to exclude it from the analysis. And then for the output, we also introduce dimension reduction, but with different reasons. So most of the output of systems are correlated to each other. So that means if we estimate one output, then we have good estimation on the output that has high correlation with that specific output. So based on this, we can reduce the dimension of output. And also there are other issues like whether our UQ algorithm, the assumption that our UQ algorithm takes is actually describes our actual model. But this is separate discussion. So today we will focus on how global sensitivity analysis can help us reduce the input number of input parameters. And while doing that, we have some challenges, like when we have high dimensional outputs, and also our computational simulation model is expensive, so we can run only few number of simulations. So this will be the focus of today's talk. So what do we do in global sensitivity analysis is when we have this kind of uncertainty in the input parameters, and when we have this output uncertainty, the variance of these output parameters can be decomposed into several pieces, which describes like how much of this variance is attributed to certain parameter. So, for example, the green variable x in this figure shows only small contribution to the response quantity, and if this is what we observe from sensitivity analysis, then we would like to exclude this in our further analysis. This because we know that this including this will not really affect the response variability. On the other hand, if we are aiming to reduce the uncertainty in the outputs, then we will want to investigate more time and resources in reducing the uncertainty in these two parameters, because those are now guaranteed to reduce the output uncertainty. And there are more details on the global sensitivity analysis. We have some materials in SimCenter website, such as previous 5 expert tips. And we recently uploaded some educational module materials that has more details on the concept of global sensitivity analysis. But all of this applies for the one single output quantity of interest. However, our real-world application example is not that simple. Let us consider the simulation, computational simulation of cyclic loading test of a material model. So we have some, and let us consider input controlled simulation. So we have input strain provided as representing the load. And then there are uncertainty in the material model parameters. So by running a simulation model written in OpenSys, we can get output of the response, which will be stress time history. So given a fixed strain time history, we still get uncertain output because our model parameters are uncertain. So in this case, each discretized time step, the stress response at each discretized time step, it becomes the quantity of interest. And in this problem, we have dimension of 342. Then how can we perform sensitivity analysis with the time history of uncertainties? I can think of 3 approaches to solve this problem. First is to simply change the output quantities of interest. And this is, in many cases, this is practically very useful because in the end, what we are really interested in is often only the peak response or maybe average response. So if we decide to change the quantities of to a peak response, for example, peak tensile stress or peak compression stress, then we will get a single sensitivity. We can perform two sensitivity analysis to get each sensitivity indices corresponding to each output of interest. However, if we really want to get the overall sensitivity indices considering actual time history of the response, then we can run sensitivity analysis at each time step separately, and then finally draw this kind of figure. So here, this figure shows you how sensitivity of each parameter changes as the time step increases. So, and by doing so, we can learn more insight about our model. For example, by inspecting this figure, we can notice that there are some time ranges that one of the parameters stands out. And this is the strain hardening ratio of the material models. And if we inspect the strain curve, that is the time period where we are imposing compression of force to our element. So it kind of tell you that when a material is getting compression load, then some of the parameter will really affect the response, while other parameter will not be very influential. So this gives you a nice insight on the problem, and understanding on your models. However, when you want to do a decision making, then probably you will want to have more compact, maybe a single sensitivity index values that can represent the overall behavior throughout the time step. And then they can average out the sensitivity at different time steps. And this is called aggregated sensitivity index indices. So how do we average out these sensitivity index values at different time steps? And this is by weighted average of the component sensitivity indices. And then weights are proportional to the variance. If you see this figure, we can see that in different time steps, we have different level of variances. So if we have higher variances, then we want to weight more in that particular time period. And then this is the example result of the problem we had with this material model. So this plot is the aggregated sensitivity index. And then in summary, when we have high dimensional output, we can either change the output quantity of interest to maybe peak, average response, or even residual response, depending on our goal of performing sensitivity analysis. And then otherwise, you can run sensitivity analysis separately for each time step, for each output quantities of interest. And then by aggregating those responses, you can get aggregated sensitivity indices. And those are just really alternative approaches depending on your purpose of sensitivity analysis. And in today's talk, I want to go more with the second approach, because running sensitivity analysis for each different output quantities of interest can be computationally intensive, especially when output dimension is high. So there is an algorithm we implemented in quoFEM, which is called principal component analysis and probability model-based global sensitivity analysis. And as its name implies, it has two major components to increase the efficiency of sensitivity analysis. So first one is principal component analysis, which is used to reduce the dimension of outputs. And this achieves this by utilizing the correlation between the output quantities of interest. What does it mean? How correlation can help us to reduce the dimension is we can first consider response at a single time step. And then we can also think of the response at the time step right behind the previous one. And we can because our stress time history is expected to be smooth enough, we can expect that these two quantities of interest will always give us similar quantity. So if we draw the sample realizations of this sigma j and sigma j plus 1 in two-dimensional space, we will observe something like this linear trend behavior. And if our data set is light in this linear, almost linear line, then we actually don't need these two axes to describe this data set. What we need to do is just rotate the axis a bit such that every data set kind of is distributed along the this new axis. And then if we know the angle of rotation, we can just read the coordinate of this data set on the new axis, and we can almost reconstruct the original data values. So, and now we need only one coordinate to express the same kind of data set. So this is how principal component analysis works. So this is intuitive when we have low dimensional data set, but when we have high dimensional data set, it's hard to imagine this subspace of the larger dimensions. So what I like to, the perspective I like to introduce to interpret this high dimensional PCA is that to drawing analogy to the conventional methods such as Fourier transform or modal analysis. So in those methods, they introduce some basis function to describe the basic function form. And then by identifying the right coefficient, we can describe the full, we can reconstruct the original function. And exactly the same thing is done by running principal component analysis. So we first identify the mean of our response, and then for the remaining residuals, we identify the basis function that can best describe the remaining residuals. So by having, for example, in this example, by having these 7 basis functions, we can almost fully reconstruct the original time history of stress curve, time history of stress. So here is saying that our original stress values, which is dimension of 342, is a linear combination of mean time history and some linear combination of basis functions. So because these basis functions are fixed, if we know these 7 W values, then we can fully reproduce the output quantities of interest. And that means this information on these 7 variable realizations is sufficient to describe this original 342 dimension space variable. So we just reduced the dimension from 342 to 7 by introducing principal component analysis. And then what this algorithm does is to run sensitivity analysis for these W variables instead of original quantities of interest, which is just 7 dimension of 7. And then reconstruct the original sensitivity index values based on this linear relationship between W and Z. And this part is relatively straightforward. And then to further increase the efficiency, when mapping between input to the reduced dimension output, when running sensitivity analysis for the reduced dimension output, we introduce probability-based, something called probability model-based GSA, which can be more efficient than performing just Monte Carlo simulations. but this one was already covered in the previous live expert tip videos, and we also provide many references in our user manual. So I will skip this part in this presentation, but this is really on how to perform the sensitivity analysis more efficiently. And you can learn more about this PCA-PSA algorithm from this reference. And then now we will move on to storm surge example. So until now, we saw a material model that has 7 parameters and 342 output quantities of interest. Now we want to scale up this to another model, which have like 2 million outputs and 4 random parameters. And this model will be storm surge simulation. So what we are aiming here is that when there is hurricane approaching to the country, then we have some observations of the past trajectory of the hurricane, and we want to predict what will be the future trajectory, and then we want to assess what will be the impact of those hurricanes. So this is hurricane. This is the model that predicts the storm surge, like water elevation, based on the parameter of hurricane, which includes storm size, storm intensity, cross-track variation, and along-track variation. And then this is some of the example of the peak water elevation obtained by simulation. So here we can see that depending on the random combinations of these 4 parameters, we can see different like regions are more affected depending on the parameter realizations. And here we can see the grid meshes, which was used to simulate the response. And as we get close to the coastal line, we get more denser grid. So in total, we have 2 million grid points, which makes our dimension of analysis to be high. So if we were performing this GSA in a naive way, what we will do is to simulate many times from input to output relationship, and then we run global sensitivity analysis for each different output quantities, and that will mean we need to repeat this for 2 million times, which is impossible. So what we are introducing in quoFEM is that we try to solve this in 2-step process. The first step is that we run storm surge simulations to obtain 500 Monte Carlo data samples. And based on these 500 realizations of output, we can run principal component analysis to get the reduced dimension variable. In this case, we were able to reduce the dimension from 2 million to 45, which is an affordable amount of output quantity. And then what we do is to run global sensitivity analysis instead of to W instead of Z. So we run GSA 45 times to get sensitivity indices for each random reduced dimension output. And then based on the linear relationship between Z and W, which PCA provides, we can easily reconstruct the original sensitivity values based on the reduced dimension sensitivity values. There was the part of presentation, and now I want to move on to the live demo. So first we will see the quoFEM user interface. So in the C drive, I made the folder called SimCenter, and there I have the quoFEM program saved. So if we open up our tool, this is the user interface you will see. And then what our high dimensional GSA algorithm is under SimCenter UQ engine, sensitivity analysis, import data files option. Actually, we can either import our model here and then run Monte Carlo to get the data samples of input and output, but we can also directly import data files. So for today's presentation, I will show you how we can do this one. And for this, we need to know what is the number of samples and what are the random variable, what are the paths to the random variable samples and quantities of interest samples, which is output, model output. So here we get either comma separated file or tab separated file or binary files. But because we have large data set, binary files will be much faster when we try to read in from our program. So I will show you the example of binary file, how we can create binary files using MATLAB, and then also how we can post-process our sensitivity results using MATLAB. And I shared all the files in the Google Drive. So please feel free to try out using the data set and also MATLAB script I provided in this link. And then, so this is the MATLAB, the data file in a MATLAB data format, which contains the information on the input samples and output samples. So I already loaded this file because I was worried it might take a long time to load, but it took only 30 seconds. First, when you load the data, you can see there are 3 variables. So first one shows you the coordinate of grid points, and then the samples are values realization of input parameters. So we have 500 realizations, so its size is 5 by 4. And Y is the samples of output quantities of interest, which is 500 by 2 million. And then first we can see how the sample realization looks like. And this shows the peak elevation, how spatial distribution of peak elevation, and the sample realization number is 8. So if you change this number, you will see different realizations among these 500 samples. And then, so this part creates the input binary file that can be used in quoFEM. Because our samples have the size of number of samples by number of dimension, we want to transpose it. This is because MATLAB uses column major binary order, but our program uses row major binary order. So, but it's easy because we can only we can just transpose this data value, and by running this, we will create 2 binary files that can be directly imported in quoFEM. And because this QI is pretty large, I think it's 3.5 gigabytes, so it will take some time to write the file. And this is done now. Now we are ready to run quoFEM analysis. So we know that we have 500 samples, and our random variables can be imported from the binary file we just wrote. I saved it in here, and this is the binary file we just created. It says it calculates the number of elements and tells you there are 4 random variables detected, so they automatically filled in 4 random variables. But I want to change the name of this because I know what they represent. First one is storm size. Second is cross variability. And second is a long track variability. And the last one is storm intensity. And then we want to remove all of these random variables. And then we will upload these QI values. And because it's it reads the number of elements, it will tell you that you need to have QI that has size of 2 million. So in EDP tab, we can say peak elevation with size of 1.6. And then we are ready to run the analysis. In the FEM tab, we select none because we don't need simulation. In this case, because we directly provided the data set. So this is all we need to run the analysis, but it will take 5 minutes to run the analysis. So here I already ran the analysis this morning and prepared the results. So after 5 minutes, what we will see is this result panel. Here it's showing you the aggregated sensitivity analysis. First, we can see that all the input are the same as what we just wrote. And then what we will see is the aggregated surge elevation, sensitivity analysis for peak surge elevation. And you can see that the second variable, which is cross track variability, is dominating the storm surge simulation. And it also shows you how long it took to run the analysis. And then it says PCA is performed to reduce the dimension of output. And 99% of total variance is reconstructed using 45 principal components. And because the data table is too large, we don't display component sensitivity indices in this case. So instead, we can save the results file in the data file, same folder. Which will also take some time only because the data table is too large. And now these super indices are saved in this output file. I will not open this file because this is large, but I can show you an example of the previous example, which was the material model. So what the structure of the output file is just a big table with sensitivity that contains sensitivity values of each output, each parameters for each output quantities of interest. And we provide both main sensitivity index and total sensitivity index. And you can find more information about this in the documentation. So what we are going to do is to read this data table and then visualize it to see how sensitivity index is spatially distributed. So in the same script, I also provide the code to visualize the results. And this file is what we just saved from quoFEM. So it reads the sensitivity result file and saves into this variable, and then maps it with the grid point which was in the original data file. So if we visualize this, and we can see that the spatial distribution of sensitivity indices. And here you can see that as expected from the aggregated sensitivity index results, the cross-track variability shows high sensitivity values, especially in certain areas. And also, if you inspect this part, then you can see that in certain regions, storm surge is, along track variability has higher influence, while in other regions, storm surge, storm size parameter is more affecting, more influential for the peak water elevation. So those are the insight what we can get from the sensitivity analysis. And this just shows you the same response. Same analysis results. And then I think that concludes my talk on the global sensitivity analysis of high dimensional outputs. Regarding quoFEM, we are continuing to improve quoFEM and trying to have more algorithms. Our upcoming release is planned to have model selection and averaging algorithm, and also multimodal and multi-fidelity Monte Carlo. So we are really trying to enhance this multiple model, to incorporate this multiple model in the UQ analysis. And then we have weekly virtual UQ office hour that you can always join and ask any kind of UQ related questions. And those, the link to our office hour can be found in the Sim Center Forum quoFEM board. And also there are more exciting upcoming live expert tips on January and February. So please check this out. I think this is end of my presentation. Thank you all for listening today.
Thank you, Songri, for the informative presentation. A lot of really interesting both examples for both hurricane and earthquake applications. So thank you for those, spending the time to go over those and explain in depth how one might go about doing this. I think, and thank you for also bringing up these other opportunities. I don't know that we have any questions for you right now, but what I want to do is remind people that if they do have questions, that there are a couple resources for them, right? Number one is we have a documentation for each of the software we produce. If you look at our webpage, simcenter.designsafe-ci.org, go to the tool page, you can find a link to the documentation. On that page, you'll also find a link to the Sim Center forum, where you'll be able to ask developers like Songri and others questions that you may encounter while you're running these tools. So I encourage you to use those resources if you have questions. And so I think at this point, Songri, we're all set to conclude. I want to say thank you again for the presentation and for preparing all the material.
Thank you, Matt.
Go ahead.
No, thank you, Matt. Yeah.
And so this will conclude today's session. Thank you for joining, and hope to see you again soon at another Sim Center Live Expert Tips.